sort of give me knowledge and background for other things I do with my life. So the educational requirements for an electrical engineer are, like most engineers, an engineering degree from a university. And in 2008, they were, the median income for an electrical engineer was about $85,000, according to the Bureau of Labor Statistics. And as far as the job outlook goes, while more jobs are expected to be created in electrical engineering, that is expected to be offset by the movement of jobs overseas. So there is expected to be little to no change in the American electrical engineering job market until 2018. So my first case study is on circuit theory, which the basic analogy that we use in our class for circuit theory to imagine electricity, because it's something that is often very difficult for people to picture, is that of water. Water in pipes as electricity is in wires. So this works for the various properties of electricity, such as voltage, which can be thought of as the pressure behind the pipes. Current, flow of electrons, can be thought of as the actual flow of water through the pipes. But combined with both of these is resistance, which is can be thought of as sort of the actual width of the pipes. So using this image, the difference in voltage or the pressure in the water. So up here there would be high pressure because it's on the other side of the pump, whereas down here, since there's nothing, there would be zero pressure. The flow would be the actual amount of water in volume of how much is actually flowing through, whereas the resistance would actually be the width of the pipe, which influences both of those things. They're all very closely connected. So in actual electrical engineering, the major component that would be thought of, I guess, as the width of the pipes would be resistors, which is the most basic component. In real life, it looks like this. They're very small. This is the size of about a wire, to give you perspective. They're measured in different strengths based on the color coding that you see here. These are two that I used of different sizes. And this is what it looks like in an actual electrical diagram. So the way circuits are actually built in the real world is on integrated circuit boards, which is those little things that just look like little boxes that are in your computers. But in an actual classroom setting, it's very difficult to work with those because they require intense factory manufacturing. So what we used is what's called a proto board, which is basically a plastic physical board with rows and columns of tiny little pinholes. So each of these pinholes is electrically connected in a different way. So the rows of each are connected in this manner, so that if you plugged a wire into this side, it would be electrically connected to one on this side. And similarly, the sides are connected in columns in the same way. And this is a picture of the protoboard that I used with a very simple circuit on it. So you can see there's the rows and the columns. And it's a very useful tool for creating circuits quickly and modifying them on the fly. So my second case study is that of digital signal processing, which is essentially just the manipulation of the actual signals that make up things like music and MP3 files or radio signals, or really any sort of a broadcast signal. And the first component that is really integral to digital signal processing is that of capacitors, which can most easily be thought of as the high-pass component, in that it expresses a resistance or impedance as a function of the actual wavelength of the electrical signal. So, the electrical signal is altering between two values, and the faster it's doing that, the higher the frequency. And the higher the frequency, the less the capacitor resists. So the higher the frequency, the more our capacitor acts like a wire. But if the frequency is a direct current, there's no frequency at all, then it would act like an open circuit and not allow any electricity through. The inductor is the opposite of this. So if there's very low frequency, then inductor lets all electricity through as if it were a wire. On an actual diagram, a capacitor looks like this, which is appropriate because a capacitor is physically built by putting two metal plates next to each other and filling them with some sort of a fluid. And an inductor is also just a literal coil of wire, which is interesting. The third component of digital signal processing that's important is that of the diode, which people know most often as in terms of an LED. But an LED is obviously not the component that is actually in any electrical systems. It's just the one that people know of. So what a diode does is it only allows electrical flow in one direction, which sounds like it wouldn't be very useful, but in fact it is integral to building actual household circuits. And electrically, it looks like this on diagrams. And this is what an actual one looks like that isn't an LED. So the way that it affects it is there's two major types of current that we talk about. And that's direct current, which is just a flat line of voltage. It looks like this if you were to graph it. And alternating current, in which the voltage with respect to time varies between two values and just like your standard sine wave. And so what diodes do, and what they have to do with this, is what's called rectifiers. So if you were to put a diode on a simple sine wave, it would actually cut off the bottoms of all of these sine waves and just leave the peaks, and simply created using just one diode. Now, that's not very useful because the goal is to get direct current out of alternating current, because direct current is what's used by appliances, whereas alternating current is how it's in the wires that you see by the road. So that's created using a full wave rectifier, which we had to build in lab. It was one of our assignments, and it was very difficult to build, but the circuit that you actually come up with is this, which I won't go through it in depth, but basically this little area right there allows the electricity to go through the rest of the circuit the same way, whether or not this is positive or negative. It's very interesting because this component is actually in every single appliance that you plug into an outlet, because it needs to get the direct current from that alternating current, which was very interesting to learn about because not a lot of the electricity stuff is very relevant, but I thought that was very neat. So my third case study is that of digital logic, which is probably the most familiar to people. The major component that people have also heard of is that of the transistor, which is the building block of all computers and watches and really most components, most electrical devices that we use nowadays. Electrically, it looks like this. It has three different ports: the base, the emitter, and the collector. The emitter is actually interesting because it's powered. It actually has a supply of power that is always being fed to it, which is different than any of the other components I've talked about. And the base, which can be thought of as the input, actually, if there's no input, then the emitter does not allow current to flow to the collector. But if there is a base voltage above a certain value, then the emitter allows electricity to flow to the collector. The effect this has is that you can actually have an input voltage that determines whether or not you have an output voltage, or what that output voltage would be. This is what a large-scale transistors looks like, but more often than not, a transistor is going to be on an integrated circuit board inside of your watches or computers or cell phones or really anything. So when you have several transistors, what they actually make is what's called logic gates. And the most basic of these is the NAND gate. And that looks like this. So this little segment, this circle on the end means not, and the half circle means and, so not and. And this is the most basic to build, and technically you could build all computers using just NAND gates, which is fascinating. But and this is what the truth table looks like. So actually what NAND means is that the output is only 0 when both inputs are 1. And in all other situations, the output is 1, which doesn't sound very useful, but a NAND gate is actually the foundation of all computers and digital circuits. The other foundation, the other building block, is that of the NOR gate. And between the NAND and the NOR gates, all circuits are built. There's no other way to build circuits other than with these NAND and NOR gates, which I find fascinating because just these two simple building blocks make up pretty much all of our digital circuitry that we enjoy on a daily basis. This is the diagram for a NOR gate, and the table is sort of the opposite of a NAND gate. in that the output is only 1 when both inputs are 0. So how these are used is in microprocessors, which is in everything from microwaves to your watches to everything. And in my opinion, is the most fascinating part of electrical engineering. So this is a, right here, this is a microprocessor, the one that I used, ATmeg 88 is what it's called. So this is it before we wired it. So each one of these little ports has a different value that we had to wire up to this switchboard and this LED board, where this was used as our input with each little switch being a 0 or 1, and all of these LEDs being the output, either being on or off. So after we actually wired it up, it looked more like this. And that is after about 5 or 6 hours of work by my lab partner and I. But, so each one of these connections determines whether or not the processor will work, and if it is not connected properly, every single one, then it does not work. And that was frustrating at times, and we actually managed to fry a few of these, which is not good because they're $15 a piece, which is bad. This is another angle, so we have wires sort of going every which way. Thank you all for being here. I'd like to thank my professor, who really taught me everything that I learned. My friends up there and back here for supporting me throughout the experience and my case studies. My parents for helping me along with everything. Mrs. Malsquay for helping me write everything. And you guys for being here. So.